So welcome back. I'm gonna, in the first few minutes, I'm going to sneak in just some repetitions about where you find information, etc. So the official website is the one which many of you have encountered. And when you're enlisted, you will also be able to access Canvas. I send weekly emails to everybody, but the same content of the weekly email is actually contained in here. So even if you haven't yet been registered properly, you can get all the information by just looking at the official website. And at the official website, you find also the link to all the teaching material, which we also went through yesterday. So I just wanted quickly to remind you of that. So sorry for repeating things, but we always have some people who were not able to be there yesterday. So I'm doing this kind of repetition the first week. There's a kind, as I said yesterday, it's a kind of professional damage. When you teach, you often repeat many things. So my daughter always teases me, saying that, Dad, I mean, you don't need to say it twice. I understood it once, right? But there's a professional damage. When you've been teaching for some 40 years, then repetition is something which becomes a part of you. Okay, so the book is in here. This is the one which I will be using. And you have the programs which you have to every single chapter. So these are Python programs which illustrate the theory. But then if you go to the lecture notes, you will find the Jupyter book. And there, every chapter is rendered as a Jupyter notebook. So if you prefer that format, that's another possibility. And then in addition, we will have the weekly material where you will find an extract of some of the programs from the different chapters and the weekly slides. So this is roughly the kind of setting I'm going to follow the rest of the semester. And in the weekly exercises, this week, there are some exercises which are essentially us practicing or reminding ourselves about linear algebra. Now, the linear algebra part is the one which, as we said yesterday, is pretty essential because quantum mechanics is a field which uses linear algebra heavily. So you will see me reminding you of some of these kind of small hidden gems in linear algebra now and then. So that was a very, very quick repeat of some of the basic, where you find the basic information. What I want to do now is to switch first to the slides. So that means this file here, and quickly remind you of some of the things we did yesterday. And then we are going to jump into the calculation of expectation values. And in particular, we're going to look at the expectation values of two particles. And we are going to use atomic helium as one of the examples. This is a case which many of you have seen before in courses in quantum physics, quantum mechanics. And that's a way to also demonstrate that the approach which we are going to take first is very little efficient. And that motivates the introduction of what we call second quantization or the number representation, where you actually freeze out the spatial degrees of freedom and other degrees of freedom, and you simply deal with the number of particles which occupy a specific state. And that's why it's called the number representation, or just second quantization. So I don't like the term second quantization because it gives you, as I said yesterday, gives the impression that there are more than just one types of quantization. But this is a kind of name which has stuck with the field. So I will use that interchangeably. So let's switch back and take a look at the slides from last week before we jump over to the whiteboard and slow down the pace a little bit. So let me just bring this up and go through some of the technicalities here. So yesterday we had a reminder of linear algebra, and we had a discussion of orthonormal basis, completeness relation, etc., etc. So I just wanted to flash through in some 5 minutes many of the concepts which we discussed yesterday. Some of the questions which you see there are questions which I will leave to you for self-study. So I'm not going to go through everything here, because I mean, there's a lot of information, and some of this is something which is obviously left for you to look at. So orthonormal basis is something which plays a very important role, because when we have such a basis, we can both define the completeness relation. This basis is often the solution to a specific problem which we can solve, hopefully analytically, or in an efficient way numerically. So it doesn't need to be something which we can solve analytically, but something we can solve by standard methods like diagonalization. And then this basis, hopefully, that basis is something which has some connections with the physical case which we are looking at. And when you have that basis, then you can always expand it, and you have the overlap coefficients, which will actually be the matrix elements of a unitary matrix, so that you have a unitary transformation. So orthonormal basis, you don't need to write down this because you have it there. And this orthonormal basis is actually something which can be, the typical situation is that if a single particle basis is a meaningful approximation, it's meaningful in atomic physics, partly nuclear physics, and some fields of condensed matter physics, if the interaction is weak. Then as you can build up a basis based on a single particle basis. And this could be like the hydrogen atom solution. It could be a harmonic oscillator, etc., as you can see here. So like examples, the typical examples which many of you have encountered are problems like these, which allow for an analytically or a numerically available solution. And this single particle basis which you have is typically the starting point for many body methods. So this is the entry point. And you will often see, if you do a Hartree-Fock calculation, which is a variational mean field calculation, this serves as a basis, and many of these methods are called post-Hartree-Fock methods. We're coming back to this. So computationally, this is normally an eigenvalue problem. You would typically discretize on a grid or expand in a finite basis and diagonalize. And then you have other cases where there's actually in the Jupyter notebook this week, there is an example of the harmonic oscillator, which if you have time to, you could explore. Actually, one of the things I wanted to do is, so if you look at the weekly exercises this week, sometimes they don't cover 2 hours. So that means that we can also discuss the examples which we have in the Jupyter notebook during the exercise session. So the exercises are not mandatory. You don't need to hand them in, but they serve as a way to, prepare the ground for the midterms. So they normally follow the lectures, and they are meant to illustrate different aspects of the lecture and hopefully give you deeper insights. So if you look into this Jupyter notebook, which are cases we can discuss in the exercise session, that contains additional information. Then the other thing which is very important for us is actually the unitarity. So those overlap coefficients which we saw, these are actually the matrix elements of a unitary matrix, which then serve as the transformation of a state into another state. And in many body physics, as I said yesterday, these coefficients of this matrix, many of the many body methods deal with approximations to the exact coefficients. So it sounds simple, but hopefully you will see that through the semester, and I'm going to illustrate how different methods link with this expression here. So the other thing is that we will, in this course, we will stay with systems which are not so-called open system. That means that particles can escape from the system. So that means that the emission theory is what is going to be the basic theory. This is also the theory for quantum computations, because every operation is unitary and reversible. So these are also some important aspects. So in a certain sense, quantum mechanics is a deterministic theory, but it is a probabilistic deterministic theory. And then these are just unitary transformation. These are things which I'm going to skip here. You can actually look up some of these yourself. And I just wanted to bring up where we ended yesterday, because that serves as an entry point for today's lecture. So one of the things which we did yesterday was actually to couple two vectors of length 2, and we looked at the tensor products. So we looked at a system, what we called a two-level system yesterday. And with that one, we set up a new computational basis, which is then given by the tensor product of the individual computational basis. And it's actually pretty easy to see that these 4 states, they form a new orthogonal normalized basis. And these are typical examples of qubit systems, but they don't need to be qubits. These states 0 and 1 would represent some specific states of a physical system. So we are not limited to think of this as terms of qubits, but they often tend, when you see this kind of notation, it often tends to be linked up with quantum mechanical approaches like quantum computing. Now, there's one thing I wanted to say here, and that deals with the exponential wall, as we call it, or the complexity of a multidimensional space, which simply means that in principle, we have an infinite set of states which the system can reach. However, since we cannot deal with infinities, then we have to find ways to truncate the Hilbert space which we have. So if you look at the most general state of, if you think now qubits, so that means just 2 states, 0 and 1, or spin up, spin down, if you're familiar with spin systems, then the most typical state which you could have then would be something which goes like 2 of n with complex amplitudes. If you have n equals 300, that clearly exceeds the number of atoms in the observable universe. And this is just to give you a little bit of the dimensionality. Something we are coming back to, which is the topic today, is a way to represent the anti-symmetry of a state. And the simplest approximation to that, it's not the exact solution, but it's an approximation, is to use a determinant. And you would fill this determinant with single particle states, and that ends up being called a Slater determinant, after Slater, who suggested this as a way to bake in the anti-symmetry of a state. Because you know that when you change 2 columns in a determinant, the determinant changes sign. And that is going to correspond to us interchanging the positions of 2 particles. So there is a principle, Pauli's principle of anti-symmetry, which was used actually to explain the periodic system. And for systems with a spin half, the wave function, the total wave function, has to be anti-symmetric. That's the Pauli principle. So if we now look at the many-body connection here, you can quickly see that if we want to set up a system with n particles, so another word on notation, I'm going always to use the uppercase letter n to indicate the number of particles. So the number of particles which you have, they are going to fill in slots of single particle degrees of freedom. We are coming back to that on the whiteboard so that you see it more clearly. And the combinatorics then, the total possible number of arrangements, is given by this kind of standard binomial factor. And that means that you end up with, if you have 40 states or slots where you can place 1 particle, and you have 20 particles, that gives you a dimensionality of 10 to the 11. That's the possible states you can make in 40 single particle slots. Now, if you look at systems, if this was a nucleus like calcium-40, which has 20 neutrons and 20 protons, the total system would be 10 to the 11th times 10 to the 11th. That would be the total space which you can access. And that is still a very small set of degrees of freedom for a nucleus like calcium-40. Do we have any nuclear physicists here? I think we have somebody online. So it means that the full n particle Hilbert space is a tensor product of n single particle spaces. And the full configuration interaction method, which we will discuss in roughly 3 weeks, 3 to 4 weeks, that works in that space. These other methods are strategies to find the relevant low dimensional part of it. So that means we make approximations. If you do quantum computing and you think of n qubits, that represents a 2 to the n dimensional state vector. And the source of this potential power and the reason for why quantum simulations of many-body system is an interesting application. So these are just some kind of motivations, but the problem one of the problems which you will often hear me mentioning is this exponential war, or the exponential increase of degrees of freedom. So I'm going to leave this to you guys just to look at, and we can discuss that afterwards. There's also something I will come back to, which is the spectral decomposition. Does anyone remember that? The spectral decomposition of a matrix? We didn't mention it yesterday. So when you have an Hermitian operator has always real eigenvalues, and we have orthogonal eigenvectors for distinct eigenvalues, and it's diagonalizable. And then the non-trivial solutions require obviously the determinant. You're familiar with that as an eigenvalue problem. And with this I as the eigenbasis, and this P of I, the projection, which we discussed yesterday, you can actually expand any state in that basis. And that gives what's called the spectral decomposition of a specific operator, where these lambda i's are the eigenvalues of that operator. So this is a feature which we are going to use. If this is something which has slipped out of your cache memory, then a quick reboot is something which will help. And this is a feature which is often forgotten, but it's widely used in quantum mechanics. And we are going to encounter this a little bit later. So I'm just mentioning it. Okay? So you don't need to remember everything, but I put up things which are actually important for us. So if you do a many-body connection, every diagonalization of a Hamiltonian matrix is a spectral decomposition. And that's something which is worth thinking of. And functions of Hermitian operators are actually defined through the spectral decomposition. And that's a very useful property. So we are now getting into the more interesting things. And this is the starting point for today's lecture. And we will start with a Hamiltonian, which we split into a piece which we call non-interacting, which then contains, like here, only single particle operators. So these are operators which act on a single particle at a time. So that could be the kinetic energy of a particle, or all the particles, and you will simply collect the kinetic energies of every object. So this H0 part, there is no interaction. And then we have the interacting part, where we mostly are going to look at the potentials of the two-body type. That means that two particles interact at a time. And one thing which you're probably familiar with classically is the gravitational force, or the Coulomb interaction. The Coulomb attraction from a nucleus is what you typically will encounter when you start looking at the solution of the hydrogen atom. And these single particle functions, which you have here, they are actually eigenfunctions of this H0. And this H0 could be T here, which is just the kinetic energy, or you could actually have a potential which traps the particles to move in a specific way. So this could be a potential which you realize in the lab, or a potential which is set up by the attraction from the atomic nucleus in an atom. So the interacting piece, as I said, is the non-interacting piece is the one which we hope can be solved analytically or easily numerically. And then everything what makes many-body physics hard is the correction to this statement which you have here. So without H0, the total energy is the sum, and this is something which we're going to derive today. So you will see that in a two-particle case, and then we are going to pave the ground for the many-body case. However, the way we're going to approach this is not very practical. And that's something which will motivate the introduction of second quantization. So if we look at the summary from yesterday, we looked at vectors. So this is a long repetition. I hope you don't mind. There were some elements I didn't mention yesterday. So we looked at vectors, matrices, inner and outer products, the bracket notation. We defined projection operators. We looked at the Pauli matrices, unitarity, orthonormal basis. And then we discussed this with a single particle basis. So the topic today is now to look at the determinants, changing the basis, variational principle, and then expectation values of these quantities. So these are the topics for today. We will probably not cover everything, so some of this will be done also next week. So now we have the language. So the central object now is actually to introduce something which is called a Slater determinant. So what I'm going to do first is actually to remind you a little bit about determinants, because we're going to need that. So we will mainly deal with fermions, unless somebody here also wants to hear about bosons. So these are integer spin particles. But most of the applications of many body physics have normally dealt with fermionic systems, because these are those which arise most frequently. So a determinant, just to remind you of that, is now given by standard equation which you see here. So you have the different columns. And this is something you may have encountered. It's called the Leibniz representation of a determinant. I'm going to remind you of some of these things. So this deals that we permute the column indices, and the sum runs over all n factorial permutations which you can make. So I'm going to show you examples quickly now of a 2x2 case and a 3x3 case. And then you can see the possible number of permutations which you can make here. So the PI is a number of transpositions which are needed to bring a permutation back to the natural ordering. So you have to choose a specific ordering. And this becomes important when we are now looking at expectation values and the calculations of them. So keep this in mind for later, just some more minutes. There's something we call the natural ordering, and it's natural to actually look at the diagonal elements. So think of the 2x2 case. If you write out a 2x2 determinant, you know that the first term is the one which would correspond to the normal ordering. That makes sense? The next one, term here, you see now that we have interchanged columns 1 and 2. And this goes back to the expression which you have here. But there, for more than just 2, I mean, it obviously becomes a little bit more complicated. But if you plug in 2 here, you know that you have the 2 possible permutations which you can make. So one would just be the basic one, and then you have the other one, which is the one where you interchange 2 columns. That sound reasonable? Nothing dramatically new. But just keep this in mind that we are interchanging columns 1 and 2, because when we come to an ansatz for a wave function, then the columns are going to represent a specific particle. So we're actually interchanging the positions of 2 particles. So each flip of a column means for us the interchange of the positions between 2 particles. So this becomes important. And that goes a little bit back to the slide previously here, because the Hamiltonians which we deal with have specific symmetries. So we have a permutation operator, which I call Pij here. And I'm stating this without a proof, but you can find proofs of this in textbooks. So I'm just going to use that one. The Hamiltonian itself is made so that this commutation relation is respected. This obviously has important consequences in the sense that the eigenfunctions of one of the objects is also proportional with the eigenfunctions of the other one. And this permutation operator, what it does is to interchange the positions of 2 particles. And when you apply it twice, then you're back to the same state. So beta squared is 1, and beta can be plus or minus 1. And for bosons, this is equal to plus 1, and for fermions, it's equal to minus 1. And this is the way you deal with the ansatz for antisymmetric wave functions. Now, there is more to the picture than meets the eye immediately here. And that has to do with the setup of a Slater determinant, which we're coming back to. And before we do that, I wanted to say a little bit about some further technicalities about determinants. So there's a linearity in a column. And then there is also something which we call the product rule. If every element is a linear combination, which you will see when we run a Hartree-Fock calculation, then we can write the new determinant as a determinant B times a determinant C. And this is actually the single most important algebraic fact this week. And try to look at that for n equal to 2 here, that this is actually the case. So this is a very important property, the product rule of determinants. So I'm just reminding you of this. And if you go into that other textbooks, Szabo and Ostlund, you will actually see in chapter 1 that there is a quite extensive repetition of some basic linear algebra elements. So what you see here is actually taken from that textbook. Evaluating a determinant from the permutation sum is not the way you would do that. So when you're evaluating the determinant, you would typically use LU decomposition. And those of you who have taken a course in computational physics or numerical mathematics, you have probably encountered the lower upper decomposition of a matrix. This is something you can do only if the matrix is invertible. If not, you would have to do a singular value decomposition. So you would never calculate the determinant using the rule which you are given when you take a course in linear algebra, because that's highly inefficient. So the way you evaluate determinants is by this way. So this is where we are going to start today, because we're going now to jump into the whiteboard. So I just wanted to bring up these elements so that you have some hooks you can put them on and go back to, because there are some things which you may have seen in courses, but which may also be forgotten. But I wanted to say a little bit here about what you see here. So this is an ansatz for the wave function. It's not the exact solution. It's an ansatz based on the single particle picture. So these guys which you see here, they are solutions to this non-interacting part of the Hamiltonian. So this could be things like the hydrogen-like wave functions. So I'm going to put up this example with helium, and we're going to go through that one so that you see clearly the connection between a single particle basis and the ansatz. So what you see here is not going to be the exact solution, but we are making something, an ansatz for the solution, which contains the antisymmetry. And the antisymmetry is then given to us by the determinant. The factor 1 over n is a normalization factor because we are looking at all possible permutations. So at the end, we would have to then divide by n divided by n factorial. So this is just a normalization factor. So keep in mind now that interchanging two particles interchanges two columns, and the sign flips. So the wave function is antisymmetric. Two particles in the same orbital give two identical rows, and then the determinant vanishes. So that's not accepted. Now, the Pauli principle does not say anything about single particle degrees of freedom. This is often a misunderstanding in the literature, because some people refer to the Pauli principle as the second bullet point here, that two particles cannot be in the same orbital. Is that the way you've heard of the Pauli principle? It can be confusing because that is a consequence of the Pauli principle if you adopt a single particle basis. So if I adopt a single particle basis, I can make this ansatz with a determinant. And then the consequence is that if two particles are in the same orbitals, then you get two identical rows, and then we know that the determinant has to vanish. So no two fermions in the same single particle state. That is a consequence of the Pauli principle, which simply states that the total wave function has to be antisymmetric. It's a consequence if we adopt a single particle picture. Okay? So if somebody asks, what does the Pauli principle say? The Pauli principle says that the total wave function should be antisymmetric. But we are going to use a single particle picture. Yeah? To be antisymmetric means that suppose now you have your state is represented by the function x. And when you mirror that to the negative side, it becomes minus x. That's it. If it's symmetric around 0. If it's antisymmetric, it just changes sign when you switch the negative values. So the antisymmetry is a postulate which Pauli came with, and it's a postulate about nature, but there is still today no experiment which defies the Pauli principle down to experimental precision. So even it's a postulate and we cannot prove it mathematically, we accept that as a postulate about nature. And the way to encompass it is typically by making an ansatz, because we don't know the exact solution. Okay? So now we're going to look at the calculations here. So let me switch back to the whiteboard. And this is where we're going to practice these things. So let me just do that. So we are now going to look at the system of two particles, okay? So in order to get started. And we are going to use that, and we're going to calculate the energy in a brute force way. So our case here, so we have a ansatz for the wave functions, ansatz for the wave function, WF, actually I should say state function, because wave function we often intend also time dependence for the wave functions and expectation value of energy. So the example we are going to look at is a case with n equal to 2. And we're going to think of atomic helium. And the case we will specialize to then is atomic helium. We're not going to put in any explicit expression for the wave functions. We were just going to leave those as just a symbol psi, and then we're just going to use that. So n equal 2. And if we think of atomic helium, we have now a Hamiltonian here, H, which we are going to define in terms of a non-interacting piece plus an interacting piece. Now, the non-interacting piece is going to be given by two one-body operators. So this is going to be x1 plus h0 of x2. So there are two particles. So we sum from I equal 1 up to n equal 2 of h0 of x of I. Now, x of I, I'm actually going to use that as a kind of compact notation here. So x of I includes the spatial degrees of freedom given by the positions of the particle and the spin of the particle. So in our case, the spin value, sigma I, is given by 1/2. And we have spin projections, m sigma I, which are given by, sorry, it should be an equal sign, equal to plus minus 1/2. And this is something which we will often label as just spin up and spin down. So these are the spin orientation. So relative to an axis, which is going to be the z-axis. I guess this is something which most of you have seen before, right? So that means that if I now take this one body Hamiltonian here, x of I, and act on this on a state, x of I, this has an eigenvalue, which I'm going to call epsilon alpha times psi of alpha of x. So this is a problem which we can solve. And we know that for atomic helium, we could use the hydrogen-like wave functions. So let me quickly remind you of that. So hydrogen-like wave functions. This is an ansatz. It's not the exact solution if I were to solve a two-body problem for atomic helium. But I can use that as a basis because I can solve the equations analytically, and I can make an ansatz that atomic helium with 2 electrons is not that different from hydrogen with 1 electron. So this is a kind of basic idea, but it's an ansatz, okay? So if we have hydrogen-like orbitals, so we typically call these solutions for orbitals or states, then we know that H0 of x of I is given by the kinetic energy operator, 2 of m, the mass of the particle, the second derivative. So the Laplacian here is something which you've seen. You can do that in the spherical coordinates where you can actually solve it analytically. And then we have a term here which is given by the interaction between the given electron and the atomic nucleus. So the atomic nucleus has a charge of C. I'm leaving out other constants, so I'm just going to call this for a constant gamma, which is not interesting here now, and then divided by R of I. And R of I is actually R of I is the distance from the atomic nucleus, which in this case is just a proton if we look at hydrogen, a nucleus, and the electron. So if you want to make a graph here, you could think of the atomic nucleus, which is much heavier than the electron, as an object which is almost at rest compared to the electron. So you could think of the atomic nucleus as your central mass frame, and then the electron is moving around here, and then we have a distance here which is given by R of I. And obviously when I write only R of I, that is going to be given by x of I, the distance in the x coordinate, plus y of I, plus z of I squared. If we are in 2 dimensions, we only have x and y, okay? So these functions, which we have here, they do actually have exact analytical solutions. Let me quickly remind you of the solutions here. So is it okay if let's just wait a little bit before I change page here. Okay, I can change page. So if you look at these wave functions, psi of alpha of x, now I'm going to break it down into a spatial part and a spin part. So this alpha represents a set of quantum numbers. This is the number of nodes, -1, the orbital momentum, the projection of the orbital momentum. It has spin, and it has the spin projection. So that means that this wave function is normally written out as a tensor product between one part, which deals with the spatial degrees of freedom and specific quantum numbers. It's the spherical coordinate R. So when you don't see vectors, these are actually the absolute values. And multiplied, or tensor product, with a spin part. And the spin part is typically given by those functions which we looked at yesterday. So this could be either 1, 0 or 0, 1. And then you would typically represent this one as a spin up state or a spin down state, which essentially means for spin half object, this is a spin 1/2, and the other one is minus 1/2. So this should be minus here. Let me just write it properly so that it doesn't confuse you. Okay. You will often see this written in a more compact way. So the compact way, which we are going to use if we use the bracket formalism, is that this phi alpha of x would typically be written simply as alpha. So alpha is now a slot which contains specific quantum numbers. And this is what we are going to use now to build up this Slater determinant and the ansatz for the ground state of the system. So keep in mind that these functions here, they do have analytical solutions. So this phi of alpha of x, if I now look at only the phi of NL, this part here, because the spin part lives in its known space, this is given by something which is called a Laguerre polynomial. So I'm not going to write them down, but it's a Laguerre polynomial, which then depends on N and L and the spherical coordinate R, or just the radius as we call it. It has another function which is called a spherical harmonic, which deals with the angles. So that contains M and ML, and theta and phi. These are the spherical coordinates for the angles. And finally, it's multiplied with e to the minus some parameter which we are going to call for beta, which is proportional to the Bohr radius and other physical constants, multiplied with r. So if you were to solve the differential equations or the Schrödinger equation for one particle, you can actually show that the analytical solution for that type of potential, that means the potential which you see here, is then given by this specific functions here. Does that ring a bell for some of you? You've probably seen this if you took a course in quantum mechanics. For us, this is not so important now. What is important for us is that this problem here has an analytical solution. So what we're going to do now, when we want to use hydrogen-like orbitals to make an approximation for atomic helium, we are now going to set up the states which you get and their energies. So if you think back to atomic physics, and I guess everybody here except those of you who never taken quantum physics, you probably encountered these quantum numbers, and these date back to Bohr. So when Bohr introduced the atomic model, you have the first low-lying state, which is a 1s. So this is an atomic physics notation. So where 1 here represents the quantum number n, s represents the quantum number L, which is equal to 0, which means also that ml is equal to 0. So this 1s state has an energy which also has an analytical expression. And we just label it epsilon 1, and it's given by some physical constants divided by this number n squared. So this is also something where we have an analytical solution. Then, so let's now set up atomic helium here. Now in Bohr's model, what you have next is a new state in energy. So now we are looking at energy here. And that provides a natural classification for the states. So the energy here, we have a 2s state, which we are going to label epsilon 2. If we don't lift any degeneracies, this is degenerate with a state which is called 2p. So this, by the way, this state has n equal to 2. These are the quantum numbers, and ml equal to 0. Sorry, 0. But then, since we have an interaction, the degeneracy gets a little bit lifted. So we have a 2p states, which are all degenerate. And here we have epsilon 3. Now, these states have n equal to 2. So there's one node. So n minus 1 gives the node of the wave function, where you just change sign. So that means that 2p is an antisymmetric state for single particle state. And then L equal to 1. And then I have ML, which now can take values -1, 0, and +1. And this continues. So the next one would be a 3s. So this is just a reminder of a almost Bohr's atomic model. In principle, there's an infinite basis. So one of the reasons why many quantum chemists normally don't use these basis sets here is because they always give you bound states. That means energies which are negative, and they correspond to states which are always bound. A physical system, you can ionize it. That means you can kick out an electron. And then that will just be kicked out and it doesn't feel the attraction from the atomic nucleus anymore. Now, before we take a break, I'm going to do a new thing. So now we're going to take this Pauli principle, which states that since these are well-defined quantum numbers, we cannot have more than one particle there. However, we can have spin up and spin down. So we can accommodate 2 electrons in the 1s state. And then we can accommodate 2 electrons here as well. Now, in this case, in the 3p case, we have actually 3 values of the orbital momentum projection along a z-axis. So it's 3 values plus spin, we have 6 possibilities. So that means for the 2p state, we actually have spin up for ml minus 1, spin down, spin up, spin down, and then finally for ml plus 1, we have a final set with spin up and spin down. Now, what you see here now is that these are going to make a natural numbering for us. So I'm going to mark them as boxes. So each one of these are boxes where I'm going to put a number. So in my ordering now, this is state 1. So when you have a vector which you have stored, that points to these quantum numbers. This is obviously state 2. So this is just a number I chosen. This is state 3. This is state 4. And then you can go on like this, state 5, etc., etc. Then I'm going to make an ansatz for the ground state of the system. And that ansatz is based on the single particle energies. So this state 1s is the one which gives the lowest energy. I have 2 electrons. So my ansatz, which we will look at after the break, is now me placing 2 electrons here. And I say now that this is my ansatz for the ground state of the system, because this energy here is actually much lower than the energy I get if I place 2 electrons here. What is much lower or less lower is something which depends on the scale. But on the scale of hydrogen-like orbitals, this will be something like 70 electron volts, which is a lot. I think it's, no, not 70, 40 something. So you make an ansatz, and we are going to build up a wave function now, which is based on these 2 guys here only, these 2 states. But you see the way we are going to set up systems here is that we are going to look at what the independent or the single particle motion gives us. And then we build a basis, a many-body basis, based on that. That sound reasonable? Now it's time to take a small break. I went a little bit over time because I just wanted to get here, because you're going to see this kind of figure again and again and again, because that's going to define the effective Hilbert spaces we will deal with. Because at some point here, we cannot deal with infinities and we have to stop. And the number of single particle slots then tells us how many combinations we can make. So let's take a small break here. Huh? So what we are going to do now, with this kind of numbering, we are going to define states according to these numbers. So instead of having all these quantum numbers, we would just put a number like 1, 2, etc. So that means that we can make an ansatz now for 2 electrons. So we want now to make an ansatz which we call phi 0 of x1 and x2. So that's particle 1 and 2. And this is going to be proportional to the state psi1 of x1 and psi2 x2. So I'm saying proportional because this does not contain the anti-symmetry. And you can quickly see that if you change sign here, now if you change the positions x1 and x2, this is just a product state, and it doesn't contain the anti-symmetry. So what we are going to do now is to use this ansatz based on what we call a Slater determinant. This is not the exact solution, but what we are going to see is that this ansatz is the eigenstate of the operator H0 acting on the state phi of x1, x2. This is going to give us epsilon 0, the non-interacting energy, multiplied with this phi 0, x1, x2. So this is a quantity which we are going to calculate now in a very brute force way. And then we are going to generalize this to n particles. So with 2 particles, I'm going to go through this exercise because it's good to see that. And then we are going to show how you can make this easier, still within what we normally call the standard first quantization. But then this is going also to motivate the introduction of second quantization next week. So if you look at this state now, if we now want to bake in this Pauli principle, then we have the correct normalization factor, and we're going to define a determinant where we have in the columns, we have the particles, and then we fill in the slots where each particle can be in. So this will be a phi 2 here of x1 and phi 2 of x2. So when we write it out now, this is just simply 1 over square root of 2. And then we have a phi 1 x1, phi 2 x2 minus. And this is called the exchange term, where we flip columns 1 and 2, exactly as we did with the determinant. And then we have 1, which now has x2, and 2, which has x1. Now, keep in mind that this is an ansatz. I haven't showed you that this energy here is actually an eigenenergy and that the state is an eigenstate of this one, but we're going to see that through the calculations now. So this energy epsilon 0 is going to be the addition of the single particle energies. So this epsilon 0 is now, this is an uppercase epsilon, is epsilon 1 plus epsilon 2. That's what we're going to show now. So we've placed 2 electrons or 2 particles in the 2 lowest lying slots here. And then we simply add their energies. They're not interacting here. Okay? This is an ansatz. So keep in mind that what we have made now is an ansatz which bakes in the anti-symmetry from Pauli's principle. And that's it. And then based on these ansatz, we are now going to build up a whole set of states. So keep in mind that this ansatz we made here is one of the possibilities, but we could have 1 electron here and 1 electron here. So if I look at the case with which we have here, and I stop here, suppose now that I make a barrier here, and I say that this is my last set of single particle states which I want to deal with. Then we can place 2 particles here. We can place 2 here if you want to, or 1 here, etc. So in total, in this case, we have now, if we do the counting, it's 2 here, 2 here, 6 here. That gives us 10 in total. And I add here and I have 12. So that means that the number of single particle slots is equal to 12. And then I have 2 particles. That means that my possibility with this kind of truncated space is given by the number of states, the possible ways I can distribute these particles, and we call these configurations, the way we can configure a system. So, or configurations, so this becomes synonymous. This is simply given by this number n over n. And in this case, this is given by 12 factorial divided by 12 minus 2, which is n. And then it's n factorial, which is 2 in our case. So here we have n equal 2 and n equal to 12. So you see that quickly in this case, the total number of possibilities which we have, if we take, so it's factorial 12, so we have 11 times 12 divided by 1 times 2. So in total, this is 66 states. If I add more particles, you see that this grows quickly. If I have 4 here, this is going to be a much larger number. And there you see again the exponential wall, as long as we don't truncate properly here. So this kind of truncation which we make has also to be physically meaningful. So there are 2 ways we are going to truncate the number of states. One is to truncate in the single particle basis. But another thing we could do now, instead of dealing with 66 states, I could say that I'm only interested in the lowest lying 10 many-body states. So you can truncate in the single particle basis, and you can also truncate in the many-body basis. And the different methods which we are going to discuss, they introduce one or the other variants of these types of truncations. So this is the exponential wall. And you can show that this binomial factor grows exponentially for the problems which we deal with. Okay? So this is just an anticipation of the problems which we are going to face. Now, what we are going to do now is to calculate expectation values. So somebody has now given us this ansatz, and now I want to calculate the expectation value of the energy. So I'm just going to set up the quantum mechanical expression for the expectation value, and that's going to be given by this kind of notation, which I'm going to write out in full detail. So we're going to take this part of the Hamiltonian first. Okay? This translates into an integral. And since we have 2 particles, this is an integral, which is an integral of x1 and x2. So let's just wait before we change page here. So mathematically, this is now given by an integral over dx1, where these coordinates typically run from minus infinity to plus infinity. And then we have the complex conjugate of the state, x1, x2 here, multiplied with the operator, and multiply with phi of x1, x2. So this is the quantum mechanical definition. There's another thing which I have anticipated already, because I have anticipated that these states are already normalized. But in principle, what you should have, if they haven't been normalized, you should also have a normalization integral here, which then will be given by phi x1, x2, or phi 0, x1, x2. So I'm assuming now that this is something you've seen before in courses in quantum mechanics, the way you write the expectation value. So what I'm going to do now is the extremely exciting exercise of writing out the Slater determinant and setting up all the integrals. So if you want to do something else while I go through the derivations, please feel free to do so. But this is something I want to do because it shows you that perhaps there are better ways of doing that, and we are going to introduce that a little bit later. And then you will see that even that better way of doing that is inconvenient, and that leads to second quantization as a compact formalism for calculating these expectation values. So we call this an expectation value when you go from a same state to the other state. And normally we would call this a transition probability if you go from one state to another state. Okay. So this is going to give us the energy, or the expectation value of the energy for that part of the Hamiltonian. So let's now start with the exciting things here. I should also mention that this integral d of x, what that actually means is an integral over the spatial degrees of freedom and a sum over the spin degrees of freedom, sigma and m sigma s. So just keep that in mind. In this case, there's only one value for s, now sigma, but you have two values for the spin projections. But we are going to use this compact notation d of x without always bringing up the spin degrees of freedom. It's always boring when you read the textbooks because they say typically it's straightforward to introduce the spin degrees of freedom, and sometimes it is not. So be always suspicious when you in a textbook see it's straightforward to see. Okay, so let's go through the calculations now. So we had a factor in front of this wave function ansatz with 1 over square root of 2. So that means that when I have two functions, this guy here is going to be given by 1 over 2, and then I have a dx1, dx2. And now I have the wave function to the left of the operator. So I have a complex conjugate, x1 psi 2 of x2 minus, and then I have the exchange term. And that's, sorry. And this is then multiplied with h0, x1. So I'm writing out the operator of x2 here, and multiplied with the right-hand part, which is now x1 phi 2 of x2 minus phi 1 x2 and phi 2 of x1. So we're going to get 4 terms. Okay. I should also remind you of another technicality. So we have now assumed that this basis which we have chosen is an eigenbasis of H0. This means that this is an orthogonal and normalized basis. So just as a small reminder for the calculations now, one of the things you need to keep in mind is that if I take the overlaps between phi I and phi j, this is going to be given by delta ij. And just quick reminder that h0 of xi acting on phi I of, so let's just put a j here just to make a distinction. This is epsilon j times phi j of xi. So we need these two details. So let's look at the terms now. So let's take the first term. And I'm going to skip the integral sign just to make things simpler. But if you look at the first term, I'm going to take this term and multiply it with that term. Okay? So the first term is going to give me 1/2. And then I have a dx1, dx2 here. And this is multiplied with psi 1, x1, psi 2, x2 here, and multiplied with h0, x1, plus h0, x2, and applied to. So these operators act on the right-hand side of this integral, the terms in the integrand, sorry. So if I now look at this integral, if I take the term with x1 here, one of these terms, that is going to give us 1/2, and then I have a dx1, and then I have phi 1 x1 and h0 x1. This is one of the terms, and phi 1 x1, and then I have dx2, and this is just multiplied with phi 2 x2 and phi 2 x2. Okay. So you see now quickly that this one is something we can take from here. So that gives us simply 1. In this case, this acts on this state. And that gives us epsilon 1 times phi 1 x1. Then, since this is just a constant, we can just put it outside. And then I have an integral of phi 1 with itself, where we simply use a normalization. So that term, this term which you see here, gives us simply epsilon 1. Then I have a similar term plus h2, h0 of x2 here, which comes from this part of the operator, which acts on phi 2 x2, and that's going to give us epsilon 2. Okay? Does that make sense? So I get two terms. I have a factor of a half. The other thing I can do now, if I look at the last terms which I have, suppose I take this one, so that term which you see here, with that one, that has a minus and a minus. But you see now the x2 part will be acted upon that one. That will give me epsilon 1 as an expectation value. But then I have a two term here, which has x1, which will be acted upon that one. So this term, which you see here, this one and that one, is also going to give me exactly the same as epsilon 1 plus epsilon 2. So I'm going to have two terms which give me the same and a factor of half in front of each. And that's going to give me simply a factor of 1. Then I have the cross term. And it suffices to just look at one of the cross terms. So with the cross term, the one I'm going to look at now, it's this one together with that one. So just let's look at that one, because the other one, this one with that one, will give us exactly the same answer. So let's take a look at the cross term. So that takes the exchange part. And the cross term is now given by minus. I have a factor of a half. I have the integrals dx1, dx2. And then I have a phi 1, x1, phi 2, x2, multiplied with h0, x1, plus h0, x2 here. And then this is multiplied with the phi 1, x2, and phi 2, x1. So let's take one of these terms. And so we are going to have an integral of dx1 and dx2 here with phi 1, x1, multiplied with h0, x1. But now it has phi 2, x1, and multiplied with, sorry, let me take away that integral here and put it in here, dx2 of phi 1 complex conjugate, sorry, phi 2 of x2 and multiplied with phi 1 x2. So now I have all the x dependencies correctly according to the integral, the integration variables. And what would this look like? What kind of number would I get here if you now use these two properties? What should we get here? When 1 and 2 are different. 1 is obviously different from 2, right? These are two different states. Any good suggestions? 0, right? Because we have the orthogonality of the states. We have assumed that this basis is an orthogonal basis. So this will be exactly equal to 0. But then when I calculate the operator's action on this state here, I'm going to get epsilon 2 times psi 2, but psi 2 doesn't match psi 1. So that gives me also 0. So the cross terms are going to give me 0. So the only thing which survives then is actually the, when I look at this, sorry, when I take this expectation value for two particles of H0 of phi 0, this is going to be given by epsilon1 plus epsilon2. So in general, where each one of these epsilon i's is just an integral, which is given by d of x, phi I, x, the one-body operator, x, acting on phi I of x. This is a definition of that expectation value, the single particle expectation value. Yeah?
This whole time, this is all like you're calculating the expected energy of a non-interacting system.
Yeah.
Right? So those are only zero because they're not interacting.
Yeah. So in a sense, the non-interacting case, if you think of that intuitively, it should simply add up the energies of all the non-interacting objects. So if I wanted to collect the kinetic energy of all of us here, I would simply take the kinetic energy of everyone in the audience and then just add it up, because we're not interacting. So the result you see is what you would expect intuitively.
In all this, like, what is the probability you're kind of, so expected values, usually you have a probability and support. So what is the probability here that you're like?
So you can look at the probability of one single particle, and that will be this wave function squared. But if you're looking at the probability of the two particle system, it will be this wave function phi 0 squared. Because you're asking what is the probability of finding two particles with those energies. And that's given by your ansatz for the single particle energy. Yeah?
Right. The first we have the conjugate state doesn't have the single conjugate on the.
So in the first, let me see if I've forgotten something here. So which one are you thinking of? Before, let's. Oh, sorry. This is me. This is just, thanks. We have some people with eagle eyes here. No, this is just me. If you see me forgetting things, don't hesitate. Yeah.
But so these are not interacting. But in practice they do interact.
That's the next one. That's the next term. Say it again, D.
Someone wrote in the chat.
Oh yeah. So let me just thanks for saying that. Yeah. Okay. Yeah, that's just okay. Yeah. Just thanks. So the next piece, because this is not the full Hamiltonian, the next piece is us to calculate phi 0 of the interacting piece of phi 0. So let's do that for two particles, because this is much simpler. So again, what we would have is 1/2 dx1, dx2 here. We have the bra side of the state, x1 complex conjugate. Now I have to remember to put all the signs properly. So this is 1 of x2 multiplied with 2 of x1, like that. But now we have an interaction between the particles. So we need to multiply this with a sum where the interaction goes. So we have the sum of I less than j, simply because we have no self-interactions. That sounds reasonable, right? We can interact with ourselves, but we wouldn't produce much energy using that. So the interaction, the potential energy is now given by xi, xj, and I'm going to say a little bit about that as well, because that becomes important, because it has some specific properties which are very important. So the physical interactions do actually have some symmetries, which make the calculations easier. So this is then multiplied again with phi1, x1, phi2, x2 here, minus phi1, x2, and phi2, x1, like that. So before we start calculating now, I'm going to plug in some specific symmetries. So what is very common? One is that the interaction does not depend on the spin degrees of freedom. That is a big simplification, because then when we sum over the spin values, you will see later that the states will have to have the same spin values. So the interaction doesn't change the spin. But you can have interactions which change the spin. But in the many of the examples we will see later, the interaction will not be changing the spin. So if you take a Coulomb interaction, that acts only on the spatial degrees of freedom. But we are going to take some general symmetries. So this V of xi, xj, so the two variables, is in general going to be a function of the relative distance. That is pretty common. Many natural forces, like the gravitational force or the Coulomb force, actually forces which we know from experiments depend on the relative distance between two objects. So that means that the potential is going to be a function of the relative distance. Okay? This has important consequences, because that means that Vxi, xj is given by xj, xi. So that's an important symmetry. And this is verified in nature to a very large extent. And for the cases which we are going to look at, this is a feature which we will be using again and again, okay? And that's going to simplify the integrals, because we will see that two of the integrals become equal. So let's look now, because we have four terms here, right? So the first term is actually us just taking this term with that one. So let's just look at that one. So the first term will be a factor over half, and then I have an integral dx1 and dx2. And now I cannot simplify because the potential depends on both x1 and x2. So I just have to leave the integral as it stands, and I cannot simplify it further. So that means that I have a phi1 of x1, a phi2 of x2, and now I have a v, x1 and x2, multiplied with phi1 of x1 and phi2 of x2. So unless I plug in specific values here for the functions and the potentials, I'm stuck with that one. So this is an integral we have to evaluate. Now, I'm going to write this in a more compact form. And the compact form is that I'm going to write this as 1, 2, state 1 and 2 in the bra side. And then I write it like a V here and 1, 2. So this is going to be my compact notation. So when you see this notation here, that is simply an integral which we have here. Now, the next term I'm going to look at is the multiplication of this guy with that guy. And then I'm going to use the symmetry. And what you're going to see is that this is exactly equal to this term. Because if I interchange 1 and 2, x1 and 2 here, and that means I have to interchange x1 and x2 here. So let's take a look at it. So the second term has two minus signs, so that gives a half. And then I have a dx1, a dx2 here, multiplied with phi1, x2, phi2, x1. And then it's multiplied with x1, x2. And then I have phi1, x2, and phi2, x1. So what I can do now is simply to interchange x1 with x2. Because we know that Vx1 or Vx2 is equal to Vx2, x1. Okay? And if I do that, this is exactly what I had in the previous case. This just becomes equal to this one. So the symmetry means that this interaction matrix element, which I in principle would write as 2, 1, so I will often call these matrix elements. And that the reason for that is that we are going to use these integrals to build up what we will call a Hamiltonian matrix. So you will hear me loosely calling these for matrix elements, but they are integrals. But later we are going to use these integrals in a table of matrix elements. We're going to rewrite this as a matrix. And you see that this is the same as 1, 2. So that's the symmetry of the Hamiltonian which we have. Okay. Now, let's do the third term. So the third term has what we normally call an exchange part. So we have a minus sign and we have a factor minus a half. Or I should remind you that now this should have a factor of a half. Keep that in mind. So there is a factor of a half here because we have it here. I forgot to put that up. So when we add these two together, we simply get 1. Now, if you take the exchange term here, so it's a dx1, we call it exchange term because we exchange particle 1 and 2. And then we have a phi1 complex conjugate, x1, phi2 complex conjugate, multiplied with vx1, vx2, and then this is multiplied with phi1, x2, and phi2, x1. This is also something we cannot calculate, or we don't know the value of it before we have plugged in the potential or the interaction and the wave functions. This is called an exchange term because we actually exchange x2 and x1. Now, what you would do then is just to rewrite this as a minus 1/2, and then we have 1, 2, v, 2, 1. Now, the final term, and I'm not going to write it down, is going to be equal to minus 1/2. But then I have interchanged here x1 and x2, if you look back at the expression. And that will be 2, 1, v, 1, 2. Now, in the last term, if I interchange 1 and 2, that is going to give me mathematically exactly this one. So when I collect every term here at the end, what I'm going to have is the following expression. So let's just wait a little bit so everybody has gotten time to write. So if I collect everything here, phi 0, H interaction, phi 0 is now going to be given by these integrals 1, 2, v. So these are the quantum mechanical single particle states, 1, 2 of v, 2, 1, which is the exchange. So this is normally called a direct term in the literature, and this is called the exchange term, or just a Pauli exclusion principle term, or just a Pauli term. So I will use this interchangeably, like Pauli term or exchange term, etc. So this is the result of the Pauli principle. So without the Pauli principle, we would not have had this exchange term. Then we would just have had the direct term. So this is already a type of correlation. It's a correlation due to the statistics which you've chosen. So we call this a correlation, but when we are thinking of correlation, we're actually going to look at effects which are beyond first order in the interaction. But the total energy then, if I look at that one, this is going to be given by H, the expectation value of the Hamiltonian, and phi 0. And this is going to be epsilon 1 plus epsilon 2 plus, and now I'm going to make a new thing here, introduce a new object, a new definition, which I call AS. So this subscript AS stands for anti-symmetrized. And the anti-symmetrized matrix element is going to be given by this guy minus the exchange term. So that gives a much more compact expression. So let's just bring this up. So this, and I'm going to write this in a more general way. These are just two random states, I and J, and similarly K and L. And if I put the anti-symmetry here, this means that I have the direct term, KL, minus the exchange term, LK. Now, these matrix or these integrals have some specific symmetries, which are easy to check, since we know that we know the following, that Ij V KL is equal to, since the potential is symmetric with respects to particle 1 and 2, this is equal to Ij V Lk. These are the specific integrals. So that means that if I look at these elements, Ij of VKL anti-symmetrized, this is also equal to Ji VLK anti-symmetrized. But then it's easy, and I leave that as a small exercise to show that this is equal to minus Ij VLK anti-symmetrized. And this is also equal to minus Ji V of KL anti-symmetrized. So this gives us a much more compact notation. So next week, we are going to generalize this to more than 2 particles. And what we are going to see then is that this expectation value, so with more than 2 particles, with n larger than 2, what we are going to get as an expression then is that the expectation value of the energy, where we now have this ansatz phi 0, where we fill up the lowest single particle states. So just to go back a little bit before we stop here, if you look at this table which we put up over single particle states, this one, if you now think of atomic neon, does anyone remember how many electrons atomic neon has? So the periodic table is something you should have printed in your, especially those from quantum chemistry. 10. So if I wanted to make a model for atomic neon, what I would do then is simply to fill in these 2 guys, and these 6 orbits. So I would have 1s, 2s, and 2p as atomic orbitals. And then I could make an ansatz for this state, phi 0, where I just use these 10 single particle states. Then my Slater determinant is a 10 by 10 determinant. Okay? So if I have more than 2 particles, which is so now, and we are going to show that next week, I'm going to set up the final expression. So of H, the Hamiltonian, and this is where we will start next week. You will find the answers in chapter 2, by the way, if you are impatient. This is going to be given by the sum over the single particle energies from 1 up to the number of particles I have, where we fill the lowest levels of epsilon I. These are the non-interacting energies. And we are going to label this as an epsilon 0, uppercase letter, the non-interacting energies. But then I'm going to get a new expression where I'm going to have a sum, and now I'm summing freely over all the single particle states up to those which are filled. And this is going to be given by the anti-symmetrized matrix element, IJAS. This is going to be the compact expression for the energy, which we will derive properly next week using the standard methods like we did now. And you will see that this is not very practical. And that is something I do in order to motivate second quantization. So we will do that in the first lecture next week. And then we begin with second quantization. And that's where we will stay for the rest of the semester. So you see, this is not a very exciting exercise, but it gives us a feeling of what we are doing. And that's why I bring it in. The take-ups, we will stop here. Then if you want to do something else, I mean, feel free to do so. But we can also discuss exercises and things you're interested in, etc., etc. And we stop here. Sorry, the recording stops here. But then we have the exercise session, which will not be recorded and not be available via Zoom. That's just in person. But you have the exercises at the end of chapter 1. It says exercises week 34, but you will also find them. Let me just show that to everybody, so that also those of you online can see where the exercises are. So if you go to the slides here, the weekly slides, I should have them at the end. No, that was another one. Sorry. Let me just stop it, because that was not the right file. Okay, so let me just show you. Here we are. So if you scroll down to the very end here, and you will see also there are many questions here, so feel free to look at these questions as well. And if you scroll really, really down, so some of these are just questions to what we do here, but you will find, no, I didn't put them in here, sorry. Yeah, here they are, here they are. So these are the exercises. You will typically find the exercises for the given week. So these exercises are, well, perhaps not the most difficult ones, but you will find partly the answer in the lecture notes. And feel free also to look at these different questions which I put in here. Sometimes it can actually be useful to, we didn't get time to actually look at this is roughly what we did. But next week we are going to derive the energy for many particles. Okay, should take a break here, then stretch legs, and I will just hang around here. Das guy slow. I will switch off this one.